Good morning, good afternoon, well, whenever you're watching this. All right, hello, how's things, how's life, how's it going? Again, hope everybody is staying um, active, staying busy, right? Staying healthy, right? Exercising, appropriate precautions. Yeah, the right. What we're going to look at today is right. We see here renal veins, renal arteries. Right, we had backing up. Right, if you will recall, right, looking at the urinary system, right, from the kidneys down to the ureters, into the urinary bladder. Right, last week we had looked at this entire course of the pathway, how our kidneys produce this filtrate, right, that fluid that's destined to become urine. Right, we, if we could jump into the glomerulus, right, we would enter into the filtrate, and then that filtrate travels all along the renal tubule. Right, remember this thing here, right? This structure here, right? The renal corpuscle. That's where the actual filtrate is produced. That filtrate then goes into the renal tubule, and at the renal tubule, that is where the filtrate is modified. It's not urine yet, right? If it remains in the urine, or I'm sorry, if it remains in the tubule, right, if it remains in the tubule at the end, then it will become urine, right? The various nephrons all accumulate into fewer and fewer collecting ducts. Those collecting ducts then kind of drip off of the renal papillae. They're then caught in the renal calyx. Right, remember, there's the minor calyx and the major calyx. Right, so this minor calyx acts like a funnel. It captures the urine that drips off from the minor calyx into the major calyx to renal pelvis into the ureter. Awesome. We covered all that last week. From the ureter down to the urinary bladder. Right, this guy down here. Then from the bladder, we talked about how, or the structures that the urine goes through to get from the bladder to outside of the body. Right, so that was the urethra. Now, depending on whether you're male or female, there's different portions of the urethra. But again, that's just a cliff note synopsis of what we covered last week. Today, right, this is where we are going to look at how much actual urine is produced. Right, what determines whether there's a little bit of urine? What determines if there's a lot of urine? Right, and that all has to do with, first and foremost, the blood supply. Right, our kidneys are, right, each kidney is about the size of your fist, right, give or take. That's something that's small. On average, receives right around 20 to 25% of your cardiac output, meaning around 20 to 25% of the blood your heart pumps on a given minute. 25% of that is going to the kidneys. So your kidneys receive a huge amount of blood supply, in particular to their size, right? And that has to do with the fact that, yeah, if the blood doesn't get to the kidneys cannot filter the blood. They cannot produce urine. They cannot get rid of waste products. Right? So this should be reviewed from last semester, from 121. Right, there's the right renal vein. Right here, right renal vein, inferior vena cava, left renal vein. Yeah, remember, right, the inferior vena cava, that is the big collection duct, or not collection duct, but the big collecting vessel from essentially the lower half of the body. Right, so all of the veins eventually feed into the inferior vena cava. Right, here's the left renal, here's the right renal. Down here are the arterial side. Right, here's the abdominal aorta. Branching off the abdominal aorta is the left renal artery and the right renal artery. Again, that was all review from last semester. So when we look at this, no, you are not going to have to memorize every single piece and every single vessel of this, no. But one thing to take notice of, right, is the vessels. Right up here is the renal artery. Right, the renal artery, just like it in the body, right, our heart pumps blood into the aorta. The aorta then branches into the subclavian artery, for instance. Then the subclavian artery gives rise to the axillary, then the axillary gives rise to the brachial, and then the radial, and then the ulnar. Right, the arteries get more and more plentiful, but they get smaller and smaller in size as you go further away from the heart. Same idea here. Right, as blood enters into the kidney, there's this big, huge, large vessel. Right, the renal artery. Hell, you can fit a finger in that thing, no problem. Well, that doesn't work. That's like trying to take a drink from a garden hose. Hell, I've done that before. That's like trying to take a drink from a fire hose. Way too much liquid. Right? So we have to make that vessel smaller and smaller and smaller, and that's what we're doing here. Right? As we go from renal artery to the segmental, to the interlobar, to the arcuate, they're getting smaller and smaller and smaller. Here you can see the hyphen. Yeah. Remember, this is the glomerular. This here is the renal corpuscle. The afferent arteriole brings blood into this specific structure inside of the corpuscle called the glomerulus. Right, that's right here. Right, these hyphens here, this is the actual structure, so this is the level of blood vessels associated with the renal corpuscle. Here is where we can actually have a significant impact on the GFR, what's called the glomerular filtration rate. Glomerular filtration rate literally just refers to what's the rate in which the glomerulus is producing filtrate. Right, glomerular filtration rate. The rate in which the glomerulus is filtering. Right. So there's many things which go into impacting that, and that's what we're going to look at. Just like with the cardiovascular system, right? Just like with the respiratory system, it is all, as far as the movement of air or the movement of blood for those respective systems, it is all based upon pressure. So too is the movement and the production of filtrate within the corpuscle. Right? It all has to do with pressure. Okay. So, glomerular blood hydrostatic pressure. Oh God, easy. I've used this example before. Take a flat, dilapidated hose, cheap one. Hook it up to a spigot. Turn the spigot on. As water is rushing through the hose begins to expand. If you're like, oh, I've never used a garden hose before. All right. Think of a balloon. Think of a long tubular balloon that some clown or not to say that it would only be clowns. I just don't actually know what you would call a person in this profession, but somebody who makes like those balloon animals, right? That big long tubular balloon. It's flat. It's dilapidated. They blow into it as air rushes into the balloon. It expands the balloon. Okay. Now imagine if there was little tiny pinholes in that balloon. As they pushed harder and harder, more air would leak out of those little tiny pinholes. Hey, that's exactly what blood hydrostatic pressure is. The blood comes in through the afferent arteriole. Right. As it rushes into the afferent arteriole, it enters into the glomerulus, and the greater amount of pressure it pushes with, the more fluid, the more filtrate that is produced. So there's a balance, right? It's kind of what's the net difference between blood hydrostatic pressure, capsular hydrostatic pressure, and then blood colloid osmotic pressure. This one here, capsular hydrostatic pressure, that one we really don't look at quite so much because that doesn't change. That's just basically the resiliency of this capsule itself, right? Like for instance, when you stretch a rubber band, even though you're like, oh, it's super easy, you don't feel any of the force or you don't feel any of the resistance, right? But as you stretch a rubber band, it's resisting that motion, right? All the elastic fibers and whatnot are trying to resist that stretching. Same idea here, when we talk about capsular pressure, right, that's the amount of pressure that essentially this capsule is resisting or kind of recoiling, if you want to think of it that way. So because it's recoiling, that's kind of pushing the filtrate back into the glomerulus. But as long as blood hydrostatic pressure is greater, right, so let's just look at these two numbers here, 55 and 15. Oh, all right, well, this is still 40, right, 40 millimeters of mercury greater, so we're still going to have more filtrate produced. Awesome. Okay. Big. Well, now we can throw something called blood colloid osmotic pressure. You may also see it called oncotic pressure. This is pressure which is derived from essentially the molecules within the blood, right? Really, by and large, mainly the proteins. Right? Remember? Oh, I know we're going to go back. We all remember diffusion, and we probably are going to all remember osmosis. I've talked about them both numerous times. But when we talk about, right, the movement of water, actually let's back up. Let's say here's a membrane, right? There's little tiny holes in this membrane. If there's a bunch of sodium here, I've done this example a bunch of times. Give me a second. So there's 2 sodiums on each side of the membrane. Let's say there's 1 water here. And it doesn't matter how many waters are over here. Let's just draw 1. If a sodium crosses the membrane, remember, water is a follower. So that means water is going to also cross over. Same idea here. So as more molecules like sodium, I gotta work on those arrows, my God almighty. As more sodium or potassium, chloride, whatever it happens to be, leaves the glomerulus and enters into the Bowman space, water is going to follow. Now, when we look at blood colloid osmotic pressure, there's a certain degree, because of the concentration of the fluid, right? If there's a greater number of molecules, right, within this filtrate, via diffusion, they're going to want to re-enter back into the glomerulus. Alright, because remember, wherever there's a higher number of, let's just call it sodium or potassium, right, or where there's a greater level of proteins, right, there's always going to be pressure drawing that fluid back in, right? Proteins. Remember, we talked about the example. Let's say here is a membrane. Let's just call it, this is the membrane of the glomerulus. This is the size of the pore inside of it. Let's say here's a protein. Is that going to fit? Nope, that's not going to fit. So proteins remain in the blood. They remain in the bloodstream. They remain in the glomerulus. They remain in the glomerulus. Due to the fact that they remain in the glomerulus, right, something called oncotic pressure is created. So what that means is basically the pulling force created by the proteins. Right, because think about it. Proteins cannot leave the glomerulus. Can't do it. Come on, let me do it. I want out. Nope, sorry. Can't do it. proteins, they must remain in the bloodstream, meaning they must remain in the glomerulus. Well, if more and more water leaves, because sodium, potassium, glucose, etc., what happens to the concentration of proteins in the blood within the glomerulus? Oh, it elevates. So because levels of proteins in the blood begin to elevate, that then draws more water back into the glomerulus. You're like, well, wait a second, if more water is drawn back into the glomerulus, doesn't that mean levels of sodium and potassium, etc., would increase in Bowman's space? Yep. Absolutely. That is why this is a never-ending revolving door of constant motion, of constant movement. Right? Like, literally, like, these are all, it could really just make them all kind of cyclic. Right? As sodium and potassium leave, water leaves, and it goes on and on and on. Right? But anyways, the end purpose, or the end game, end goal, whatever, it's all the difference. It's the net difference. Right? So if, for instance, if 2 and 3, right, let me get some rid of this here. 2 and 3, they are causing fluid to be drawn back into the glomerulus. Blood hydrostatics pushing outwards. So it's a net gain. These two here equal 45. This equals 55. So there's a net difference of 10. Meaning there's 10 more units of pressure pushing outwards into Bowman's space. Awesome. Does that make sense? In lecture, we will talk about that. Well, whoever you have for lecture, you'll definitely talk about that more so. But why that's important? Right, sure, it is the production of urine, but the movement of molecules also has to do with the ability of the kidney, specifically the nephron, to adjust the concentration of the urine. If I just drank a bunch of water, or just drank a bunch of liquid, if I just drank 8 glasses of water, do I need to retain 64 ounces of water? No. So I'm going to need to get rid of large amounts of that. Well, one of the things is, well, along with the urine, there's a small amount of what are called solutes, right? I've been talking about sodium, potassium, chloride, etc. Yeah, things that are dissolved in water are just solutes. They're things dissolved in water. So there's going to be a greater amount of solutes. So we need to try to make that urine as dilute as possible, carrying as few of those solutes as possible, right? Because just because we just drank 8 glasses of water, so we need to get rid of a large amount of water, that doesn't mean we need to get rid of large amounts of sodium, glucose, potassium, chloride, etc. Alright. So when we look at, like, this number here, right, 300, 350, 550, 750, 950, no, you do not, absolutely not need to measure or memorize these numbers, not at all. The whole point of this is the concentration, even if at the end of the line the urine is super dilute, meaning it has very few particles in it outside of water. It wasn't formed that dilute. Right? It didn't form of only, let's just, again, talking about numbers, it didn't form with only 65 particles. I don't remember the exact measurement. Let's just call it 65 particles per million. Again, the number is completely arbitrary. Right? 65 particles per million. Right here, initially, let's say it began right around 300. As it goes through the tubule, remember, as we travel through the tubule, certain points along the tubule, water is reabsorbed, sodium is reabsorbed, potassium, glucose, amino acids are reabsorbed. And there's certain parts along the tubule where water isn't able to move. There are certain parts of the tubule where the wall is impermeable to water. Right? So the fact that along the tubule, right, the fact that there are certain parts of a tubule which are impermeable to certain molecules, sodium, potassium, water, what have you. Right. We can see, right, when we look here, right, we can see, like, for instance, the number here, right, this is the concentration within the actual, this part of the nephron, right, so outside of the tubule, right, this is the concentration, let's just call it 750 particles per million. Right. With the ascending limb, or basically from here upwards, the ascending limb, again, that's impermeable to water. Right, so it's impermeable to water. Well, why does that matter? Why does that make a difference? Because do we see how within the tubule, right, do we see how, right, the particles within the tubule, right, there's a much lesser concentration, right? For instance, 550, 750, 350, 550, 150, 350. All right, so if these particles, for instance, call it sodium, potassium, whatever you want it to be, right? When they enter into the tubule, right, water is going to follow. Right. I'm sorry. Let me erase that. I drew that arrow backwards. There we go. As the filtrate is traveling up the tubule, the reason why, right, this number here of particles is decreasing is because it's leaving. Right? Right, the sodium, the potassium, the magnesium, whatever it happens to be, is leaving the tubule, right, as this number is going down. Water would follow, but it cannot. Right, water can't follow because this part of the tubule is impermeable to water. Meaning water cannot cross. It's like Gandalf from Lord of the Rings. You shall not pass. I know that movie came out in 2001. Most of you were like, "What is that?" Check it out. We've all got time. Great movie, great trilogy. Anyways, but does that make sense? So, right, the fact that along the tubule, certain parts of it are impermeable and permeable to certain molecules, that's what allows it to adjust the concentration of the urine. Here, same idea, but just flip-flopped. Right, we talk about a concentrated urine. So again, like I mentioned, the numbers are arbitrary, right? Let's just say, 1,200, particles per million. Again, completely made up. But when we look, we see how along this first portion of the tubule, right, water leaves in huge amounts, and that significantly increases the concentration of the filtrate. As that filtrate ascends, right, well, particles begin to leave. Alright, well, water isn't, right, water can't leave the proximal convoluted tubule. I'm sorry. Water cannot leave the ascending limb. Right? But one thing it can do is it can leave the collecting duct. Remember the hormone, antidiuretic hormone? right? Anti-diuretic. Okay, retain water, retain fluid. Yeah, that's where it has its impact, right? Anti-diuretic hormone impacts the collecting duct, and it allows water to cross over. Right, just think about it. Even though water is unable to leave the ascending limb here, the different solutes can. As the different solutes leave the tubule, well, water's a follower, and water follows. The beautiful part is that along the collecting duct, the various solutes are impermeable, and they can't follow along with H2O and leave. They must remain inside of the collecting duct. Hence the reason why we're able to adjust the concentration, and in this example we have a much more concentrated urine. Right. Now, obviously, this really is depends upon the amount, right, of fluid you intake. Now, even if you the idea that we need to drink 64 ounces of water in a given day is kind of based on nothing, right? If you are somebody who is does a significant amount of exercise, works outside, does for whatever reason sweating a lot, that sort of thing, okay, right? I could see somebody drinking 8 glasses of water, but for just random Joe Blow who's sitting inside, desk worker, how much fluid are they losing? Pretty tiny, pretty small amount. One of the other things which influences how well our renal tubules work, how well our renal corpuscle works, right, is any sort of renal disease. Right, if somebody has renal hypertension, for instance, right, we're going to just briefly talk about it. What happens if a greater amount of blood enters into the afferent arteriole? If a greater amount enters into the afferent arteriole, do we produce more or less filtrate? Take about 8 seconds and think about it. Well, if I make this number bigger, then that means if none of these other ones change, that means I'm going to produce a greater amount of filtrate. Which, oh, awesome, I'm producing more urine. Well, you're producing more filtrate, which means if you have a greater amount of fluid getting into the glomerulus, you increase the hydrostatic pressure. That means you're actually producing more filtrate than you probably need to. Right? Depending on the level of hypertension or the level of renal disease, right, the pressure might be significant enough, or the damage to the glomerulus might be significant enough that proteins start to get lost through the urine. Right, that's a problem, because now proteins are going to be drawing more and more fluid into the glomerulus, or into the glomerular space. If more fluid is drawn into the glomerular space, that just even further increases the damage to the kidney, right? The damage to the glomerulus, because it's overly stretching the glomerular capsule and causing damage. Right? Somebody who has diabetes, right? Especially uncontrolled diabetes, right? The glomeruli are very, very small, delicate capillaries. Diabetes, especially uncontrolled diabetes, just wreaks havoc on these things. Right? It absolutely just destroys the glomeruli. So when that happens, we start to produce huge amounts of filtrate. Again, which increases the pressure here. Right? At the same token, right, blood colloid osmotic pressure. Right? Now, blood colloid osmotic pressure, right, actually would begin to decrease. Right? Onconic pressure, the pressure driven by the proteins in the blood. Right? Blood color osmotic pressure would actually decrease, because if more, what drives this is all of the different solutes and particles dissolved in the blood. If because of renal disease, because of renal hypertension, right, if more molecules are getting out of the bloodstream, that means there's fewer particles left in the bloodstream. If there's fewer particles left in the bloodstream, that means this pressure is going to go down. Right, so it's all a pressure game. All right. That finishes up, right, what we had to cover with the urinary system. The next presentation, we are going to be getting into the reproductive chapters.